Good morning. Welcome to Krishna's classroom. We do the second part of the talk entitled Geometry of Linear Functions. Before we go further, let us first recall the content of what we did very quickly. So we started with R2 and R3, or we made an analysis of both R2 and R. So start with first one. We took x equal to R2 over R. It's a two-dimensional linear space. It's a two-dimensional linear space. So we do our work on that. The two-dimensional linear space. Now we have f, a linear function defined from x to R, which is a linear map from x to the associated field R, and we assume f is not equal. Before we proceed further, we take the case f identically equal to 0 is a linear function but with null space the whole so we shall assume f not equal to 0. So this is something which is not, there is nothing much to talk about it. So we say f is a non-zero linear function. It's a non-zero linear function. Now let us take the null space of this. So let us define NF to be a set of all x belonging to R2 with f of x this is called the null space. NF is a one-dimensional subspace of X. And in fact, you know that what are the one-dimensional subspaces? That is times in R2 passing through the origin. So NF is a line that passes through the origin. Now it's easy to see this if P1, P2 is the standard ordered basis, for R2, any x R2 is of the form x equal to x1 e1 e2, and we identify this with the ordered pair x1. This is the coordinates, what you call the coordinates of x. E2. Then f is linear, therefore f of x is equal to x1 into f e1 plus x2 f e2. And now set which is a scalar f of e2. Then f of x equal to e2, and nf is then equal to set of all x1 x2 in R2 such that a1 x1 a2, which is line through the orbit. So this is the scenario that you have this, and then some line through the origin. This is a1 x1 plus a2 x2 equal to c. So call this L. So let us designate this by L. Now this came from an F, therefore this is equal to what do you call where f is a linear function on R. So this is, it represents a line. Okay. Thus NF is a one-dimensional subspace of R2 which is a so that's the important observation. remark F is completely determined by its at a second remark which I don't want to write, I want to remind you is that there is no sanctity for using E1 and E2 as the basis. You can use any two linearly independent vectors in R2 to craft the whole of R2. As you know, using parallelogram law, you can make linear combinations of those vectors and reach out to all the vectors. So this is the scenario that you have. Okay. Now, the question that you ask at this stage is the following. Given a linear space, so we have seen that given a linear function, there is a linear subspace of R2 determined by it. So the question that you ask is this: given a one-dimensional subspace R2 0 is it determined by a linear. Determined in the sense that null space of the line. The given subspace. So that's the question. So first we observe that given a linear functional, it determines a subspace, a line passing through the origin, which is a one-dimensional subspace of R. Now the converse question we are asking now, given a one-dimensional subspace of R2, that means a line passing through the origin, is it determined by a linear function on R2? If so, how do you get hold of this particular linear function? So this is what we were exploring. So let the given line be set of all x1 such that A1 x1 equal to 0, and we want f not 0, not equal to 0. So we insist on A1 square plus not equal to 0, so that both A1 and A2 are not simultaneously 0. So that L is subspace of R. Now, you see, this is the scenario. This is your L. Now, you can find a vector B not on the subspace. There exists a B not equal to 0, B not belonging to L, so that B is also not equal to 0. Such that any vector is resolved uniquely as the sum of a vector in R2, in L and a scalar multiple of B. So the geometry is that you have a vector space spanned by right, this is B, and these are scalar multiples of B. This is the vector space spanned by B. Let me put it this way, or if you want, you can call this L prime. So you take, what you do is you take any vector in R2 and resolve it as the sum of a vector in L prime and a vector in L. This is possible. We will show that this is possible. What you do is draw a line parallel to this one. So you complete the parallelogram with the edges lying in L and L prime. Then this point is some k times B, and this is some x prime. How do we do that? How do we fix this? That is, x prime is uniquely fixed, k is also uniquely fixed. How do you do that? Okay, now we will take this one, we will see, is it possible? So let us determine, if possible, let us k such that x minus kb belongs to L. Okay, that is, we want, that is f of equal to 0 and f being linear, which implies fx minus k times fb equal to 0. But fb is not equal to 0 because b does not belong to. Therefore, what you can do? So set a equal to, which is well defined, sorry, x prime equal to x minus then f of x prime equal to 0, because it is, you just compute this is equal to x prime belongs to M. So hence the resolution is of equal to x prime this is the resolution, and this is unique. I mean, you can show that it's unique. Okay, so such a resolution is possible. Now we shall do the following. Now this is the backward how to find this b. Okay. So let us just keep it keep it our side. Now let me define the form. So given x, okay, given x, we will sorry, belonging to R2 then x you write as x prime plus k times b. Okay, for some k, right? Now define f of x equal to, by fixing equal to that. So that is possible. Okay, right? Just verify. So if you take some one x1 and sorry, one x and x tilde, and then work out its. So here x prime belongs to, okay, define fx equal to k equal to 0. That is true. I mean, that's what we have seen. Okay, right? Then f is a linear function on R. That's easy to show. You take two vectors x and y. So x equal to x prime plus kb y equal to y prime plus k k1b k2b, where x prime and y prime belong to the subspace L. So you define a map from, so this map is defined from with these properties. Then you can actually show that f of null space of is that is f of prime. Okay, so that's it. So what you have is, given a vector in R2, you can actually construct a linear function whose null space is the given subspace. Now let us take the next case. So we take the case 2. Once again, you will see that, so fb from x, so over R, three-dimensional. Suppose f from x to R is a linear function. Then you see that null space of f is a plane passing through the so NF now assume f is non-trivial. That means f is not equal to 0. And this is a plane in R3 passing through the origin. Once again, you can prove this, that the converse question you can ask. Conversely, suppose a plane is given. Does there exist a linear functional on R3 the null space of the given this is the question that you are asking. Okay. Once again, suppose this is given, then you can set. So, since M is two-dimensional, there exists a vector b not equal to 0 in R3 B does not belong to then any x belonging to R3 can be resolved uniquely as in M and a scalar multiple of B. That means x now set by f of 0 so K is uniquely set. Therefore, what you have the following. Equal to is equal to right. So for each x there is a x prime and a k. So you have verified that linear function with null space of f zero right. So that is the analysis that you right. So the inference is that from these two examples it's clear that a linear function on R2 or R3 determines a plane line or a plane passing through the and vice versa. Okay, now you see that the null space in R2 is a one-dimensional subspace. When you come to R3, it becomes a two-dimensional subspace. And if you pursue the same analysis, if you take Rn, then it is going to be an n by n minus 1 dimensional subspace. Okay. So what is the observation that we make is that the null space of a linear functional, at least in the finite dimensional vector spaces, is a subspace of dimension 1 less than the dimension of the space. Okay. So this is what we conclude. So we observe that the null space is a subspace in general is a linear function then the null space of f or you say that the codimension of see, when you work on infinite dimensional spaces, this does not make any sense. I mean, this statement does not. This is something that is specifically suitable for this. So we have to reinvent the state the the language to express the analogous concept in the infinite dimensional spaces. So let us start working. Right? Is it possible have a infinite dimensions? So we have to give a meaning for this. You can say that the codimension of the null space of F is 1. That seems to be fairly good expression. And observe that the null spaces we have been considering are proper subspaces proper subspaces having no proper state. That means its maximal proper space. So this is the important property. So we have to work with vector spaces or subspaces which are of codimension 1, which is equivalent to saying that they are maximal proper subspaces. Okay, we say that let X be a over K. K stands for depending on whether the space is a real space or a complex space. Maximal proper subspace of X if there exists an element such that the span of that means every vector in X can be written as a sum of a vector in M and a scalar multiple of A uniquely. Okay, so this is the meaning. This is what you mean by a maximal proper subspace. Now we shall state the main theorem, which is a generalization of the result that we have seen on R2 and non-zero then the statement that we make is this. Let f be a linear function on X and f not equal to 0. Equal to 0. It's also called a hyperspace. Hyperspace. F is determined by the null space of F and the value of element not in M. Second statement is the converse of that. If M is a hyperspace x, that means a maximal proper that's the meaning. Where x is a linear functional f on x such that okay, let us prove this. Since f is a non-zero linear functional, zero. So it's a proper subspace of. Now let A belonging to X be such that not equal to 0. Now consider an element x prime defined by minus then f of x prime equal to zero. Therefore, what you have? You have x prime belongs to it. So this is the breakup of any x. And here x prime is in M. and FA is not equal to 0, and this is what. Okay. So what do you have? Get x equal to or span of this is equal to x. Okay. So you have any vector in X can be written as a linear combination of a vector in M and a scalar multiple. That is so that completes the proof of the first part. In fact, we prove that this is uniquely determined by now we prove that f is uniquely determined by M and the value of f suppose G is a linear such that the null space of G is equal to M, which is equal to null space of F, and then what you have, Gx is equal to G of x prime plus Ga. Now this is equal to which is equal to this proves the uniqueness of the linear function or proves the what you call that the linear function is completely determined by its null space and the value of f at some element not in the null space. F at the point now we prove the converse. Hyperspace and so there exists such a consider and there exists a unique belonging to M K such that now define and remember this K differs, K and X prime are different for different X. Therefore, at each point you can define this. Okay? Thus, linear. It's easy because you see that if X and Y is another vector, then it is Y prime plus, and this is K1A, the other one is K2A, and then f of X is equal to K1, f of Y equal to K2, and then you can easily show that f is linear, right? There is no problem, and I can just record it. this is equal to because you get x plus y equal to y prime plus this belongs to so that completes the proof of the theorem. I just conclude with one example of an infinite dimension. A set of all when X is a linear space, now any P is of the form e to the power n. This is the nth degree polynomial, the typical nth degree polynomial. Define equal to P naught, the first scalar. The coefficient of e to the power 0 you define as the value of e under f. Then f is linear if it's a linear function on x. What is the null space? The null space of f equal to 0. Okay. Now this is a proper subspace of ER because this consists of all polynomials with the coefficient of t to the power 0 equal to 0. It's a proper subspace of, for instance, 1. Okay, and you see that the span of That's very easy to see. Okay. Therefore, NF is a hyper and you can just mimic the whole theory on this easily. So this is an example of an infinite dimensional space. Note that. P square so I think that completes the discussion. I want to make one more remark. Suppose you take the geometry of, and this is the null space. This is the null space L, given subspace. Now you see that given A, consider to L passing through A. This is the vector A. So this is L plus, and you have in fact R2 equal to L plus A and L plus A equal to B minus A belongs to A. So this is an observation. Okay. Therefore, you see that these are just see, these are not disjoint as it is, but connected by this relation. Okay. So you can say that you can split the vectors into an equivalence classes using the subspace L. Okay. Then write down the. Okay. So that is an observation. So you see that this vector space can be stratified as the union of parallel lines. In R3, M is a two-dimensional subspace. Therefore, you can conceive M plus A for A not in M as a plane parallel to M passing through A. Okay, so you get sort of planes stacked one over the on top of the other and covering the whole three-dimensional space. Okay, so likewise similar analysis you can do on every one of these. So that is the geometry of the dimensions, right? So the important point is that at every point on this line, the value of f is the same. Okay, so f is a constant on this line. So we just write it like that. Takes a constant value. Okay, right? Similarly, this is in R2. In R3, you take m plus a, then f of x is equal. Similar analysis. So, thank you very much. Conclude the lecture here. Now, I think we have some supporting geometry to look at the Banach theorems. And wherever it is possible to give a geometry interpretation, we'll try to do that. Thank you very much.